Back in 1910, if you walked into the Wright Company factory in Dayton, Ohio, you wouldn't believe what you were seeing. This wasn't some shiny modern assembly line. This was basically a big wooden barn where 20 guys were building machines that could fly. The Wright Model B represents something pretty incredible. It was America's first production airplane. Not a one-off experiment, not a prototype, an actual product you could buy, with specifications, with a price tag, with a warranty. And every single one was built by hand. So here's what we're going to do. We're walking through this factory floor by floor, station by station. We're going to see exactly how they took raw lumber and metal and turned it into an airplane. Every cut, every measurement, every technique. Because this is where modern aviation was actually born. Not at Kitty Hawk, but right here in this workshop. Before anyone picks up a saw or fires up a lathe, everything starts at the drawing board. And in 1910, that meant exactly what it sounds like, an actual wooden board with paper stretched across it. The Wright Company employed 3 full-time draftsmen. These guys worked in a separate room on the second floor, away from the sawdust and noise of the shop floor. Natural light came through tall windows. The room always smelled like India ink and paper sizing. Now, here's the thing about these drawings. They weren't like modern CAD blueprints with every dimension spelled out to 3 decimal places. The Wrights worked from what they called pattern drawings. These showed the overall shape and major dimensions, but a lot of the actual construction relied on master patterns, physical templates made from thin sheets of zinc or hardened steel. The draftsman would create full-scale drawings of every wing rib, every strut, every fitting. Then a pattern maker, usually the most experienced woodworker in the shop, would transfer those drawings onto metal sheets. He'd cut these sheets with heavy metal shears and then file each curve, each angle, until the pattern was perfect. These master patterns were guarded like gold. They hung on the wall in a locked room. Because if you lost or damaged a master pattern, all production stopped. Every wing rib had to be identical. Every strut had to be exactly the same length. A bad pattern meant bad airplanes. And here's something that'll surprise you. They checked these patterns constantly. Once a week, the quality supervisor would pull the patterns and measure them against the original drawings. Because metal expands and contracts with temperature. Ohio has hot summers and cold winters. A 1/10 of an inch change in a pattern could ruin weeks of work. So now we've got our patterns. Time to start the actual construction. And that means wood. The Model B used 2 main types of wood, red spruce and white ash. But this wasn't just any spruce or any ash. The Wrights were obsessive about wood quality. The spruce came from the Appalachian Mountains of West Virginia. Specifically, they bought from a company called the West Virginia Spruce Lumber Company. In March 1904, Wilbur Wright wrote them a letter that still exists today. He asked for 500 feet of the finest possible spruce, entirely free from knots, with straight grain and free from twist. See, red spruce, Picea rubens is the scientific name, has a strength-to-weight ratio that's almost magical. It's light as styrofoam, but strong as steel when cut correctly. But it only works if there are no knots. A knot is where a branch grew out from the trunk, and at that point, the wood fibers twist and cross. Under stress, that's where wood cracks. When the train cars arrived in Dayton loaded with lumber, the Wright Company's chief inspector was there. Every shipment, no exceptions. He'd walk along the stacks of boards, pulling random samples. He checked for knots. He checked the grain direction. The fibers had to run perfectly straight from one end to the other. He checked the color. Light reddish-brown meant fast, healthy growth. If a board failed inspection, it went to a separate pile. These boards were still good wood. They'd use them to make shipping crates and storage racks, but never, ever would they go into an airplane. The Prune boards then went to the drying room. This was a heated room at the back of the factory. The wood had to dry to a moisture content of about 12%. Too wet and it weighed too much. Plus, it could warp later. Too dry and it would become brittle. They tested moisture using a simple but effective method. They take a small sample, weigh it on a precision scale, then bake it in an oven for 2 hours at 220 degrees Fahrenheit. Weigh it again. The difference was water. Simple math gave you the moisture percentage. Now, white ash was different. Ash is heavier than spruce, about 50% heavier. But it has one crucial property: you can bend it. And more importantly, when you bend ash, it retains most of its strength. The Wrights used spruce for all the straight parts: wing spars, struts, supports. They used ash for anything that needed to be curved: wing ribs, curved braces, irregular shaped pieces. The wood shop was the heart of the operation. 12 woodworkers labored here, surrounded by machines that would look familiar to any carpenter today, with one big difference: precision. The floor was covered in sawdust. The windows stayed open even in winter because wood dust could explode if it got too concentrated in the air. The noise was constant: the whine of saws, the hum of mechanical planers, the hiss of the belts connecting everything to a single steam engine. First station, the bandsaw. This was a continuous 15-foot steel blade running on 2 enormous wheels. The bandsaw operator would cut rough lumber into approximately the right size pieces: wing spars, struts, structural members. But here's where it gets interesting. Every cut had to be perfectly square. The saw operator had a metal square, a device that ensured the blade cut at exactly 90 degrees. He'd check that square at the start of every shift. If it was off by even a 60th of an inch, he'd stop and readjust the saw. From the bandsaw, pieces went to the planer station. Here, a mechanical planer removed small shavings of wood, smoothing the surface and bringing the piece to its exact dimensions. The planer operator worked to tolerances of 1/32nd of an inch. That's thinner than a sheet of paper. How did they achieve this precision? Micrometers. The Wright Company had invested in precision German micrometers, instruments that could measure to thousandths of an inch. Every 5 pieces, the operator would stop and measure. If dimensions started to drift, he'd adjust the planer immediately. For the curved wing ribs, which were made of ash, the process was totally different. First, they had to soften the wood. They did this with steam. There was a steam box in the corner of the shop, basically a big wooden coffin connected to a boiling water kettle. The ash strips would go inside this box for 30 to 40 minutes. The hot steam penetrated the wood fibers, making them pliable. When they came out of the steam box, the strips were hot and soft. The craftsman had to work fast. He had maybe 5 minutes before the wood cooled and hardened again. He'd clamp one end of the strip to a metal jig, a mold in the exact shape of the wing rib. Then, carefully, he'd bend the wood around the jig, securing it with clamps every few inches. The wood stayed clamped in the jig for 24 hours. During that time, it cooled, and the lignin, the natural compounds in wood, set in the new shape. When you removed the clamps the next day, the wood held the curve perfectly. But here's the trick: not all ribs had the same curve. The Model B had 16 ribs in each wing, and each one was slightly different. The rib at the wing root, where it connected to the fuselage, had a deep curve. The ribs at the wing tips were almost flat. So the Wright Company had 16 different bending jigs, each numbered and cataloged. While the woodworkers were creating the wooden structure, another group of guys was working with metal. And when I say working with metal, I mean creating every bolt, every bracket, every fitting by hand. The metal shop was in a separate building. They had to keep sparks from metalwork away from flammable sawdust. 5 blacksmiths and machinists worked here, and their boss was a guy named Charlie Taylor. Now, Charlie Taylor deserves his own documentary. This guy was the real deal, a born mechanic who could build just about anything. He's the one who built the first airplane engine for the Wrights in 1903. Built it in 6 weeks from a solid block of aluminum using nothing but a lathe, a drill press, and some hand tools. For the Model B, Taylor's team manufactured hundreds of different parts. Wing brackets, small L-shaped pieces where the wooden struts connected to the spars. Cable turnbuckles, threaded devices that allowed you to adjust tension and control cables. Rudder fittings, special hinges that allowed control surfaces to move. Let's take a wing bracket as an example. It started as a flat bar of steel, about 1/8 of an inch thick, 2 inches wide, 6 inches long. First, the blacksmith would mark where the holes needed to go. He'd use a punch, a hardened steel tool with a sharp point, to make small dimples in the surface. Then it went to the drill press. This wasn't a modern handheld electric drill. This was a man-sized bench drill, powered by belts from a central shaft. The operator would clamp the metal piece in a vise on the drill table. He'd select the drill bit of the right size, usually 1/4 inch for bolt holes. Then he'd lower the bit by turning a big hand wheel. Here's the tricky part. You can't just drill through steel in one go. The bit would overheat and lose its edge. So the operator drilled in small increments, down 1/4 inch, then pull the bit out. Dip it in cutting oil to cool. Drill another 1/4 inch, cool again. It took maybe 5 minutes to make a single hole. Once the holes were drilled, the piece went to the bending bench. Here, the blacksmith used a heavy vise and a hammer to bend the metal at a 90-degree angle. This sounds simple, but getting exactly a 90-degree angle required real skill. Too little and the fitting would be loose. Too much and the wood would crack when you tightened the bolt. After being formed, the metal brackets went through heat treatment. They went into a small forge, a coal-fired furnace that could reach 1,500 degrees Fahrenheit. The metal would glow red hot, then get plunged into oil. This hardened it, making it less likely to bend or break under stress. Final step, polishing. Every metal piece was polished with rough sandpaper, then fine sandpaper, then polishing cloth. Why? 2 reasons. First, smooth surfaces are less likely to start cracks. Second, polished parts were easier to inspect. You could see any defect immediately. But all the wings in the world don't mean anything without power. And this is where Charlie Taylor really shined. In 1910, reliable aircraft engines simply didn't exist on the market. Automobile engines were too heavy. Motorcycle engines didn't have enough power. So the Wright Company made their own engines right there in the factory. The Model B's engine was an inline 4-cylinder motor mounted vertically. It produced between 30 and 35 horsepower, not much by today's standards, but revolutionary in 1910. And here's the impressive part. The entire engine, including radiator and accessories, weighed just 180 pounds. Building one of these engines took about 3 weeks and involved incredibly precise work. Let's walk through the process step by step. Step 1, the engine block. This was cast in aluminum at a local foundry, either Miami Brass Foundry or Buckeye Iron and Brass Works, both near Dayton. Now, aluminum was expensive material in 1910. It cost about 20 times more than cast iron. But it was the only metal light enough and strong enough for the job. The foundry would create a sand mold in the shape of the engine block. They'd pour molten aluminum heated to 1,200 degrees into the mold. They'd let it cool for 12 hours. When they broke open the sand mold, they had a rough engine block that weighed about 25 pounds. But that rough block was just the beginning. It had to be machined, cut and shaped to extremely tight tolerances. Charlie Taylor did this work personally on the early engines. Later, he trained a few other men, but he always supervised. The lathe they used was a massive machine made by the Cincinnati Machine Tool Company. Taylor would clamp the engine block in the chuck, the rotating device that held the workpiece. Then, carefully, moving hardened steel cutting tools, he'd machine the inside of each cylinder. The cylinders had to be exactly 4 inches in diameter, and when I say exactly, I mean within 2/1000ths of an inch. How do you achieve this precision? Slow, careful work. Taylor would make cuts of maybe 5/1000ths of an inch at a time. Then he'd stop and measure with an inside dial indicator, a precision instrument that could measure tiny differences. The pistons were made separately, also from cast aluminum.
Each piston had to fit its cylinder with a clearance of just a few thousandths of an inch. Too tight, and it created excessive friction, wasting power and generating heat. Too loose, and combustion gases leaked past, reducing compression. Taylor fitted each piston individually to its cylinder. He'd measure the cylinder, measure the piston, calculate the clearance. If it was too tight, he'd go back to the lathe and remove a few thousandths of an inch, then test again. Repeat until it was perfect. The crankshaft, the shaft that converted the piston's up and down motion into rotary motion, was a masterpiece in itself. Taylor started with a 100-pound block of steel. Yes, 100 pounds to make a part that would end up weighing maybe 15 pounds. First, he'd drill holes strategically around the block. Then he'd use a chisel to cut between the holes, removing big chunks of excess metal. What remained went to the lathe, where Taylor meticulously cut away until he created the crankshaft's complex shape, straight shafts connected by offset curves. The camshaft, the component that opened and closed the valves, was also handmade. Taylor would grind individual cams, egg-shaped lobes, and then fit them onto the shaft. Each cam had to be perfectly timed. A difference of 2 degrees and the engine wouldn't run right. Once all the individual components were made, came assembly. This was like surgery. Taylor and his assistants worked at a clean bench with every tool precisely organized. First, they'd install the main bearings, the supports that held the crankshaft. These were lined with babbitt metal, a soft alloy that allowed the crankshaft to spin freely. Then they'd carefully lower the crankshaft into place. They checked that it rotated freely with no binding spots. The pistons went in next. Each piston had rings, thin strips of metal that sealed against the cylinder wall. Installing these rings was tricky. You had to compress them, slide the piston into the cylinder, then release the rings to expand and seal. The valves went in after that. The Model B used atmospheric intake valves, a design that seems primitive to us today, but clever. The intake valve was sucked open by negative pressure when the piston moved down. It didn't need a complex mechanism to open it. The exhaust valves, however, were pushed open by push rods from the camshaft. The engine was water-cooled. That meant installing a radiator, a copper tube device mounted at the front of the engine. Water circulated by gravity and thermosiphon. Hot water rises, cold water falls. No pump needed. For ignition, they used a simple magneto system. The magneto generated electrical sparks without needing a battery. Once the engine was running, it was completely self-sufficient. When the engine was fully assembled, came the moment of truth, the first start. Taylor would fill the radiator with water, fill the fuel tank with gasoline, then he'd manually rotate the engine, checking that everything moved freely. To start, they'd prime each cylinder with a few drops of raw gasoline. Then they'd engage the magneto, and assistant would spin the propeller quickly. If everything was right, the engine would roar to life with a sound that made the shop windows rattle. But tuning was just the beginning. Taylor would spend hours tuning the engine. He'd listen carefully to each cylinder. If one was slightly out of sync, he'd adjust the valve timing. If he detected excessive vibration, he'd check the balance. An engine was only declared ready when Charlie Taylor personally approved it. And his standards were brutal. If he heard anything he didn't like, any knock, any irregular vibration, the engine went back to the bench for more work.
Now, with all the components being manufactured, let's get to what was probably the most complex part of the entire airplane, the wings. The Model B's wings had a 39-foot wingspan. That's almost 12 meters tip to tip, and they had to be built with absolute precision. A half-centimeter difference in the curve could make the airplane fly in circles. Wing construction began with the assembly table, a huge flat platform the size of an entire wing that was guaranteed to be perfectly level. The wing builders would lay out the spar patterns on this table and trace their positions. Each wing had 2 main spars, beams that ran from root to tip. These were made from the finest spruce pieces, cut from 2-inch thick boards.
The spars had to be perfectly straight and have exactly the same camber curve, the slight curvature that gave the wing lift. Once the spars were positioned, the builders started installing the ribs. Remember those 16 curved ash ribs we mentioned earlier? This is where they went. Each rib was glued and nailed in place with precise spacing. The first rib went at the wing root. The second went exactly 24 inches later. The third, another 24 inches. The builders used a metal master ruler to ensure every spacing was exact. To secure the ribs, they used a combination of fish glue and small brass nails. Fish glue, made from fish swim bladders, was heated in a double boiler until liquid. One builder would brush it on the joining surfaces, while another quickly clamped the rib in place. The nails were hammered at careful angles to avoid splitting the wood. And here's a fascinating detail. The most experienced wing builders could tell by feel and sound whether a nail was going in correctly. A slightly different sound meant the nail had hit a weak spot or was splitting the wood. After all the ribs were installed, they added vertical struts between the upper and lower spars. The Model B was a biplane, remember, 2 wings stacked one above the other. These struts connected the wings and gave the structure rigidity. Then came the really ingenious part, installing the wing warping cables. This was the control system the Wrights had patented. Instead of ailerons like modern planes, they twisted the entire wing tips to control roll. A complex network of steel cables ran through the wing structure. When the pilot moved the controls, these cables pulled the wingtips in opposite directions. The right wingtip tilted up, while the left tilted down. This created more lift on one side, making the airplane roll. Installing these cables required extreme precision. The cables ran through small metal eyelets attached to the ribs. Each cable had to have exactly the right tension, not too tight or it would deform the wing, not too loose or it wouldn't control effectively. How did they achieve the right tension? By music. Seriously, a properly tensioned steel cable makes a specific musical note when plucked. The Wright wing builders learned to recognize the exact pitch each cable should make. Too low, tighten more. Too high, loosen a bit.
So now we've got a complete wing structure. Wood, cables, everything perfectly aligned. But it's basically just the skeleton. To work as a wing, it needs a surface, and that's where muslin comes in. Muslin is thin woven cotton fabric. Think bedsheet, but lighter. Untreated, you could easily tear it with your hands. And yet, when treated correctly, it became a surprisingly effective aerodynamic surface. The Wright Company had a separate sewing room run by a woman named Ida Holdegrieve. Ida was a trained seamstress. She applied for a job listing that said plain sewing, which the newspaper corrected to plain sewing, thinking it was a typo. But the Wrights really did want someone to sew airplanes. Ida eventually supervised a crew of 5 to 7 seamstresses. These women cut and sewed the muslin into precise panels that fit over the wing structures. First, they'd unroll large boats of muslin on long cutting tables. Using the same metal patterns that guided the woodworkers, they traced the shapes of wing panels. Then, with scissors sharp as razors, they'd cut the fabric. The sewing had to be flawless. The seamstresses used special needles and waxed thread. Every stitch had to be the same size, about 1/8 of an inch. The seams had to be perfectly straight, and there couldn't be any puckers or gathers. When a panel was sewn, it went to the wing assembly crew. They'd start at one end of the wing and carefully stretch the fabric over the structure. The fabric was tacked to the ribs with small brass tacks, spaced about 2 inches apart. Stretching the fabric was an art. Too loose, and it would ripple in the airflow, creating drag. Too tight, and it would tear. 2 men worked on opposite sides of the wing, gradually pulling the fabric taut, while a third hammered in the tacks. Once the fabric was tacked down, came the varnish. They used a compound called cellulose nitrate, basically celluloid dissolved in solvent. This stuff did several things at once. First, it waterproofed the fabric. Second, it stiffened the fabric significantly.
Third, it created a smooth surface that reduced air resistance. And here's the clever part. As the varnish dried, it shrank slightly, pulling the fabric even tighter over the structure. The application process was applied with wide bore bristle brushes. An applicator would work methodically along the wing, painting the varnish in long, even strokes. The varnish had to be applied in thin coats. If you put too much on at once, it would run and create heavy spots. Each wing received 4 coats of varnish. First coat, let dry for 4 hours. Second coat, another 4 hours. Third coat, fourth coat. The whole process took about 2 days. After the varnish was fully cured, an inspector examined every square inch of the wing surface. They looked for bubbles, signs that the fabric wasn't properly adhered. They looked for wrinkles. They looked for any imperfection that might affect performance.
So now we've got all the components: covered and varnished wings, fuselage structure, tested and tuned engine, balanced propellers. Time to bring it all together into a complete airplane. Final assembly happened in the cleanest area of the factory, an open space where the entire airplane could be viewed from all angles. The floor was carefully swept before each assembly began. Even a single wood splinter could cause problems if it got stuck in a fitting or bearing. Assembly started with the central structure, what we'd call the fuselage, though on Wright planes it was more an open skeleton of timbers. This section included the rails where the pilot and passenger would sit side by side, and the mounts for the engine. The engine had to go in first because it was the heaviest part, and everything else would be positioned around it. Charlie Taylor and 2 assistants used a chain hoist to carefully lower the 180-pound engine onto its mounts. Critical alignment was absolutely critical. It had to be perfectly level, not tilted forward or back, not canted to one side, and it had to be perfectly aligned with the propeller shaft. Even a misalignment of a fraction of a degree would cause severe vibrations. Taylor used precision levels and specially made alignment fixtures. He'd place a level on the engine block, adjust the mounting brackets, tightening bolts on one side, loosening on the other. Check again, adjust more. This process could take a full day. With the engine mounted came the wings. This was a delicate operation that required 4 men, 2 on each side. The lower wing went first. The men would carefully lift it and position it over the mounting brackets. Temporary bolts held it in place. Then came measurements. The wing had to be at exactly 90 degrees to the fuselage center line. It had to be perfectly level.
Perfect.
Once the lower wing was secure, the vertical struts were installed. These wooden struts connected the upper and lower wings. Each had to be exactly the right length, 6 feet, measured to within 1/10 of an inch. The upper wing went last. This was the tricky part of assembly.
How does that look now, Charlie?
4 men had to lift the 300-pound wing, position it precisely over the tops of the struts, and lower it into place while 2 others guided the fittings. Tension cables after both wings were in place. Dozens of tension cables had to be installed.
Steady now, lads.
These cables ran diagonally between the struts, creating a truss structure that gave rigidity to the wing assembly. Each cable had a turnbuckle in the middle, a threaded device that allowed adjusting the length. The assemblers worked systematically around the airplane, tensioning each cable until it produced its characteristic musical tone. The whole process took about 6 hours.
We need to talk about the propellers because they were probably the single hardest component to make in the entire airplane. The Model B used twin propellers, 8 feet 6 inches in diameter each, rotating in opposite directions to cancel torque. And they had to be perfect. An unbalanced propeller would vibrate violently, potentially destroying the engine and airframe. Each propeller started as a laminated block of spruce. 3 layers of wood were glued together with the grain running in perpendicular directions.
The propeller
this created strength in all directions.
Lamination.
Then began the real work, carving.
The middle
A
crosswise.
specialized craftsman used extremely detailed technical drawings showing the propeller's exact profile at different points along its length.
This specific
Here's the
profile at
challenge.
Station 5
Every
shows the
part of the
transition.
propeller has
We
a
must
different
ensure
angle.
the angle is
At the
exact to
hub, where
maintain
it
the
connects
blade's
to the
efficiency
engine,
in the water.
the angle is steep, maybe 45 degrees. At the tip, it's much shallower, maybe 20 degrees. And the transition has to be a perfect, continuous curve. The craftsman worked with specially made planes, some with curved blades to match the propeller's contours. He'd remove wood and small shavings, constantly measuring against templates and checking against the drawings. Making a single propeller took about a week. This wasn't work you could rush. One cut too deep in a moment of carelessness, and you'd ruined a $50 block of wood in a week's labor. When the propeller was carved, came balancing. The propeller was mounted on a special shaft that allowed it to rotate freely. If one blade was even slightly heavier than the other, it would rotate downward. The craftsman would then remove tiny amounts of wood from the heavy side, maybe a spoonful of shavings at a time. Test again, remove a bit more, repeat until the propeller would stay balanced in any position. The finished propellers were covered with cotton duck fabric at the tips and then painted with aluminum paint. The paint wasn't just for looks, it sealed the wood against moisture and provided a smooth surface for better efficiency.
An airplane without controls is just an expensive sculpture. The Model B's controls were unique and required careful installation and adjustment. Unique control system. Unlike modern aircraft, the Model B used what the Wrights called the hip cradle. The pilot rested his hips in this device, and by moving his body sideways, he controlled the airplane's roll. Cradle mechanics. The cradle was connected to the wing warping system by a series of cables and pulleys. When the pilot leaned right, the cables pulled the right wingtips up and the left wingtips down. The airplane rolled right. Installing this system required routing dozens of cables through the airplane structure. Each cable had to run through pulleys mounted at specific points. The pulleys had to rotate freely. Any binding meant sticky or unresponsive control. Elevator. For pitch control, raising and lowering the nose, the Model B used a rear elevator. This was a change from earlier Wright models, which had the elevator at the front. Moving the elevator to the rear made the airplane more stable and easier to control. Elevator connection. The elevator was controlled by a lever beside the pilot. The lever was connected to the elevator surface by more cables and a system of wooden push rods. Push the lever forward and the nose went down. Pull back and it went up. Rudder. The vertical rudder was used to control yaw, left and right movement of the nose. On the Model B, the rudder was automatically coordinated with the wing warping system. When you leaned to make a turn, the rudder turned automatically in the same direction. Fine-tuning. After all the cables were installed, came hours of fine-tuning. The mechanics checked that each control surface moved smoothly through its full range. They checked for any binding or sticking. They adjusted cable tensions until the controls had exactly the right feel. All this meticulous work meant nothing if the final product wasn't inspected with the same rigor. And Orville Wright personally inspected every airplane before it was allowed to fly. Orville would arrive in the final assembly room with a clipboard and checklist. He'd spend the next 4 to 6 hours examining every inch of the airplane. First, the wooden structure. Orville checked every joint for cracks. He looked for any sign that wood was splitting or warping. He verified that all glue connections were solid. Then, the cables. He'd pluck each cable, listening to its tone. Cables that sounded wrong were readjusted immediately. He also visually checked every cable for frayed wires, signs of wear that could lead to failure. The fabric surfaces got special attention. Orville looked for wrinkles, loose areas, or anywhere the varnish hadn't adhered properly. He'd run his hands over the surfaces, feeling for imperfections that eyes might miss. The engine inspection was the most rigorous.
Orville personally checked the engine alignment with a precision level. He verified that all boat connections were tight. He checked the fuel system for leaks. He checked the cooling system. Then they'd start the engine.
That one
Orville
there,
would
the
stand
fourth from the
alongside,
spar.
listening
It sounds
intently as the
entirely
engine
wrong.
ran. Any unusual
Tighten the
sound,
turnbuckle
any
at
knock,
once.
any vibration, and he'd shut down the engine and
The
investigate.
tension sounds good
If
here.
Orville found anything,
See that
absolutely
spot near
anything
the
that
strut?
didn't meet his standards, the airplane went back
It
to
needs
the work
another
area.
coat of
No
varnish.
discussion, no compromises, no exceptions. This obsession with quality had a cost. The Wright Company never produced more than 4 Model B airplanes per month. Competitors who were less demanding could produce faster, cheaper. But Wright airplanes had something others didn't, a reputation for reliability that was almost legendary. Pilots knew that when they bought a Wright, they were buying an airplane that wouldn't fail in the air. And in 1910, when flying was dangerous enough already, that reliability was worth gold. So finally, after weeks of work, we've got a complete airplane that's passed Orville's inspection. But it's still not ready to fly. There are a few final steps. First, the airplane had to be partially disassembled for transport. The wings were removed and packed in special wooden crates lined with burlap. The engine was drained of oil and water. The fuselage structure was carefully strapped to a trailer. The airplane was then transported to Huffman Prairie, the Wright's testing field on the outskirts of Dayton. This was a flat field of about 80 acres, surrounded by trees and occasionally shared with grazing cows. At the field, the crew carefully reassembled the airplane. Even though it had been assembled and inspected at the factory, they checked everything again. Every bolt, every cable, every connection, because now they were about to trust their lives to this machine. The Model B's takeoff runway was just a wooden rail about 60 feet long. The airplane sat on a small wheeled cart that ran along this rail. When the airplane gained enough speed, it simply lifted off the cart and was flying. On the day of a test flight, the crew arrived at sunrise. They made a final series of checks. They verified fuel pressure. They tested ignition. They hand-cranked the propeller a few times to ensure the engine turned freely. The fuel tank, a simple 1-gallon container suspended from a wing strut, was filled with gasoline. The radiator was filled with fresh water. The engine bearings received a few drops of oil. The pilot, usually Orville in the early days, later one of the trained test pilots, made his own pre-flight inspection. He checked the controls, making sure all surfaces moved freely. He checked wind conditions. He assessed whether conditions were suitable for flying. So finally, after all these months of work, selecting wood, machining metal, sewing fabric, assembling, inspecting, came the moment of truth. The pilot climbed onto the open structure. No parachute, no seatbelt, just the pilot, the airplane, and courage. He positioned himself in the hip cradle, finding the comfortable position that would give him best control. The engine mechanic, usually Charlie Taylor, stood at the front with the propeller. The pilot would shout, "Contact!" Taylor would pull the propeller sharply downward. The engine would roar to life. Blue smoke puffed from the exhaust. The propeller became a blur. The entire airplane vibrated with contained energy. Cows in nearby fields would lift their heads, startled by the noise. The pilot let the engine warm up for a few minutes. He listened to the rhythm of the cylinders, checking that all were firing evenly. He watched the water temperature gauge, waiting until it reached operating temperature. When everything was right, the pilot signaled. The mechanics released the weights holding the launch card. The airplane started rolling along the rail, accelerating. 3 miles per hour, 10, 20. The pilot felt the structure vibrate beneath him, felt the wind start to blow against his face, felt the wings begin to generate lift. Then, about 60 feet down the rail, it happened. The cartwheels lost contact. For a split second, the airplane was still in contact with the rail. Then, complete and glorious, it was flying. The pilot pulled back gently on the controls. the nose rose. The airplane climbed to 10 feet, 20, 30. The engine's roar echoed across the fields. The machine's shadow glided over the grass below. The pilot gently tested the controls. A slight lean left. The wingtips twisted. The airplane rolled. Back to level. A lean right. The elevator lever forward, nose down. Back, nose up. Around the field, the airplane circled, gaining confidence with each turn. Below, the mechanics watched, shading their eyes against the sun, counting every second in the air. Charlie Taylor smoked a cigar, but his hands trembled slightly, a sign of how much success meant to him. After maybe 5 minutes, an eternity in emotion, an eye blink on the clock, the pilot prepared to land. He reduced throttle, slowing down. He lined up with a flat section of the field, gradually descended. 10 feet high, 5. The airplane descended until the wooden skids touched the grass. It bounced once, then settled. It rolled across the field, slowing, finally stopping about 200 feet from the touchdown point. The pilot shut down the engine. For a moment, there was just silence, glorious silence after the roar. Then the mechanics were running, shouting, laughing, slapping each other on the back. They'd done it. They'd taken raw wood and metal and turned it into something that could defy gravity. They'd built not just an airplane, but the future.